We're recording, Max. Okay, cool. Hi, everybody. Thank you so much for coming on to this tutorial about reinforcement learning and concrete problems. So, hopefully everybody's read the paper. So what I'm going to do is give a really brief overview of reinforcement learning as a whole and problems discussed in the paper, and then we'll have to talk about it and do questions later. Okay, so what is reinforcement learning? Why do we care about it? Why is it cool? The basic idea of reinforcement learning is that you have some agent, a little agent guy, and he's got actuators, which is the means by which he can interact with his environment, the world around him. He also has percepts, main sensors, stuff like that. So his eyes, his touch, his whatever, by which he can get information from the environment and then he can act on it with his actuators. Our agent also has some functions that will enable him to learn what to do given any particular state of the environment. These functions are the crux of reinforcement learning, and they consist of a reward function, which we've got to specify, which is a problem we'll get to later. So basically the reward function tells the agent how good any particular state is. So if he's at time step 1 in this particular reward learning episode, if he's at time step 1, how good is that time step and what action can he take to get to the best possible next time step? How do we know about that? We also have a value function. Take the reward function for any particular state. Say you've got some variables in your environment, variable 1, variable 2, variable 3, whatsoever, and you're trying to maximise these variables somehow. Your reward function might say, well, if all of these 3 variables are at 100, that's great. That's what we're going for. That's fantastic reward. But if taking an action that would give the agent that reward would also make it impossible for him to ever get to any other state with maximal reward, it would have a low value. So the value function here is to capture not just the reward at one possible state, but the reward of every other possible state that is accessible from the current state. How does the agent know what to do in order to maximise this value, in order to maximise its reward over all of the time steps in an episode? We have something called a policy function, which is what the agent needs to learn. This could consist of anything. It could be a very, very simple formula. It could be a really massively complicated neural network. Basically, given these inputs from the environment, what we want to do is take the action that maximises the value, given this reward function which defines the value at every state. How do we know what to do that? The policy function will tell us what to do given all the information that we've got so far. Okay, so that's your 30-second introduction to reinforcement learning. What problems might be associated with this? You know? Yeah, there's a few. Yeah. Okay, one interesting problem is exploration versus exploitation. So, given that the agent is in some environment state and it doesn't necessarily know what reward is associated with all of these states, it might know that this particular state has a reward of 100, arbitrary, but it doesn't know what these are. Should it focus on going into the state where it knows what the reward is? It knows it's a good reward. It could just stick there and stay there and stay there in states that are similar to that state in order to maximise the reward, or should it take a risk? Should it take a chance and explore these other possible states, which might have negative reward, might have possible reward, we don't know yet. We'll come back to this problem in a minute. Another interesting problem inherent in reinforcement learning is the problem of this value function, right? So the idea is that we don't only care about the reward in the next possible state, but also in the other states that are accessible from that. But how far in the future do we care? Maybe we just care about the next 2 states, but that means our agent will take actions without considering any long-term implications. Maybe we care about the next 3 states, right? Maybe we care about the next 4, maybe we care about the next million. if we care about the next million steaks, then you might end up with an agent that makes decisions that we think are really, really bad in the short term because it cares much more about the future than we do. This is relatively context dependent. So let's assume we have an optimal agent, an agent with perfect information about every single state, every single possible future state. It has its reward function, it has its value, and it's optimised its policy function such that it will always take the best possible action to maximise reward over the entire episode, over every single time step, maximise reward. Fantastic, right? That's exactly what we were looking for. But there's a whole host of problems inherent in this. So this is coming back to the concrete problems in AI safety paper, which is what I'm going to talk about now by means of a lovely example, which should hopefully make this very clear to everybody. Say you've got a cleaning robot. I wish I had a cleaning robot. You've got an Android, some kind of machine that will come into your home and clean your home and leave it absolutely spotless. How fantastic. What's the reward function for this system? Can we say for every piece of dirt, for every piece of rubbish in my flat, you get a reward of -1? That would be pretty good, right? That would motivate the machine to remove all the bits of rubbish, remove all the bits of dirt, and therefore maximise its reward function. Cool. However, there are several different problems in terms of reward specification. The first one is side effects. We've got a reward function, we've got an agent that's learned to optimise that reward function, it's learned to perfectly remove every single piece of dirt, every single piece of rubbish from my flat, fantastic. But we haven't told it about anything else in the environment in our reward specification. We haven't said, clean the flat, but while you're doing that, please don't run over my cat. Please don't burn the house down. Burning the house down is a really good way to make sure there'll be no rubbish in the future, because there'll be no house. Unwanted side effects are a huge problem, because, I mean, you can name any number of unwanted side effects that might occur, even just with this toy example of the cleaning robot. It might run over your cat, it might run over you, it might break all the dishes, it might turn your bed upside down, it might do all kinds of different things, because we don't know how exactly this agent is going to learn its policy function. So there's one issue. Another one is reward hacking, which is kind of fun. So say if your agent's reward function is based on all the bits of rubbish, all the bits of dirt that it can see, a really good way of maximising that reward function, making sure that it never gets penalised again, is to destroy its own visual sensors. Problem solved, right? Yeah, maximise reward function, that's exactly what we want, but it's not really what we want. Another problem is scalable oversight. It's possible to allay a lot of these problems to do with side effects, reward hacking, stuff like that, by having some kind of overseer, okay, some kind of human feedback loop, so that every time the agent kind of goes to run over your cat, or, I don't know, throw your dirty dishes out the window or whatever, you can kind of step in and be like, oh, no, that's not what I meant, negative 100 there. And the agent will learn from that, and that's fine. But if the policy function is so complicated that you don't know why or how the agent is making these decisions, and even more importantly, in situations outside of this, frankly, rather silly toy example, if the policy function is really complicated and the agent is working a lot quicker than you're able to keep up with, there's no way to provide that kind of oversight. So that's another problem. A really interesting issue is safe exploration, which also kind of comes back to the exploration versus exploitation problem in reinforcement learning in general. Safe exploration. The whole idea of reinforcement learning is the agent will learn the optimal action to take in order to maximise its reward function, in order to reach the goal that we've specified, probably badly specified. And so experimentation is a natural part of that, right? You want it to clean your flat in the most efficient way possible. You want it to find the optimal mopping pattern to make your kitchen floor spick and span. What if in the process of finding that optimal mopping pattern, the agent's going to try lots of different things. Obviously, that's fine. It's going to start from this side, it's going to start from that side, it's going to try different cleaning solutions. Great. What if one of the things that it tries is sticking the mop in a plug? We know that that's a bad idea, but the agent has no way of knowing. We didn't specify it. How would it possibly know that that's a bad idea? And finally, the final problem raised in the concrete problems in AI safety paper is distributional shift. Even if we manage to get an agent to act optimally in my flat and not run over my cat and not electrocute itself or me or do anything else that we don't want it to do, even if it's perfect in my flat, we can't guarantee that it's going to do the same thing in your flat. You might have a dog, you might have different layout, you might have unsafe electrics. There's all kinds of reasons why you can't necessarily assume that an agent is safe in one situation is necessarily going to be safe in another. And that's the distribution shift problem. And this all kind of comes down to reward specification, right? How can we specify everything in order to create an agent that will achieve our goals and also not do any of the other stuff that we don't want it to do? This is a really, really interesting problem. In fact, I would say it's the core problem in AI safety right now. And fortunately, there's lots of clever people working on it, but we're going to talk in detail about some different approaches to reinforcement learning safety next. Cool.